Hello guys, welcome back to a new episode. This is a part 4 of the video series of how to design the most effective irrigation system for your farm. In part 1 we discussed about what is irrigation. Part 2 we've discussed various methods of irrigation. Part 3 we discussed how to choose the most effective irrigation system. And now in part 4 we are discussing about crop water requirements. So crop water requirement is a very important factor in design because it is what will determine how much water you need to apply during irrigation. So crop water requirement basically is the amount of water that is required to meet evapotranspiration rate so that crops can thrive. If there is not enough water, or the amount of water that's available is not enough for evapotranspiration, in most cases crops will start wilting and eventually die. So if you meet the evapotranspiration rate, or you apply the amount of water that is going to meet the evapotranspiration rate, then crops will survive. So this is a very important factor when you are designing an irrigation system, because it is what is going to tell you how much water you need to apply to your crops. So stay tuned till the end, because this is a very important discussion that we are having today. And it eventually it will form a very important factor in designing irrigation system. So there are various terms that are used in determining crop water requirements. We have what is called ETO, we have KC, and we have ETC. So the various terms are projected on your screen, as you can see. So the reference rate ETO is the estimate of the amount of water that is used by a well-watered grass surface that is roughly 8 to 15 centimeters in height. Evapotranspiration rate ETC represents the evapotranspiration of the crop under standard condition. What I mean by standard condition is that the crop is under any stress. Because realize stress factors such as pruning results into more water loss than when it is not stressed under such conditions. Then the crop coefficient KC is the effect of crop characteristics on water requirement. Crop characteristics such as the stage of growth, the type of crop in terms of its size and all that. So all of those factors come into play in determining how much water the crop needs. So when calculating the ETC, which is the crop water requirement, you must determine the growth stage of the crop, their duration, then you select the appropriate KC values to apply as per the formula that is there attached. So in the formula you can see that ETC is given by KC times ETO, where ETO is what we said is the reference rate, then KC is the crop factor, which is determined by the growth stage of the crop. It is determined by the type of the crop and also the climatic factors that come into play. So ETO is determined by two methods. We have evaporation pan, then we have also formulas, calculation formulas that is used in determining the ETO, the reference rate. So in pan evaporation, a pan is filled with known quantity of water and allowed to evaporate for 24 hours. Then the remaining quantity is measured. So the difference is what is known as the EPAN. So now the ETO, which is the reference rate, is given by the K-pan times the EPAN, where K-pan is the pan coefficient, which depends on the type of the pan that has been used, the pan environment, whether it has been placed in a fallow place or in a cropped area, then climatic conditions, basically the prevailing humidity and the wind speed. So for class A evaporation pan, the K-pan varies between 0.35 and 0.85 with an average K-pan of 0.7. For the sunken Colorado pan, the K-pan varies between 0.45 and 1.1 with an average K-pan of 0.8. So the details of the K-pan coefficient or the details of the pan coefficient are normally provided by the supplier of the pan. So when you buy a pan, you'll get, or the supplier of the pan will give you the appropriate coefficient that you need to use. So once you determine the appropriate K pan, then you plug into the formula that I showed you above. So in that formula, you can see ETO is given by the K pan multiplied by the E pan. So once you determine the K pan, now the E pan, again you determine which is the difference between the amount of water that you put in the pan and the remaining amount of water after 24 hours. So that difference, then you multiply the factor, which is the K pan, gives you the ETO, which is the reference rate. So then once you determine the ETO, then you'll use the KC value to determine what to call now the crop water requirement. So pan evaporation takes account issues of wind, temperature, radiation, and humidity, which are the same factors that affects the crop transpiration rate. So in determining the ETO using equation, we have two equations that are used. One is called the Penman-Monteith equation. Then we have Blandly-Cradle equation. So I'm going to put the Penman-Monteith equation in your comment. So if you can check on the comment section, you'll find that you'll read more about the Penman-Monteith equation. The one I'll focus on for purpose of this video is Blandly-Cradle equation. So Blandly-Cradle equation is the simplest, and it takes account only temperature. So when determining the ETO, which is the reference rate using the Blandly-Cradle method, is given by the formula that is shown. So in this formula, ETO is equals to P into 0.46 T mean plus 8, where ETO is the reference crop evapotranspiration in terms of millimeters per day. T mean is the mean daily temperatures in degrees centigrade. Then P is mean daily percentage of annual daytime hours. So P is determined from the table, which takes altitude into consideration. As you can see from the table, on one end we have latitude, which is the percentage degree or south of the equator where your farm is located. That can be determined even from Google Earth. Then on the other side also you can see the months. So if your crop is growing from, for example, between January and July, you can see at 60 degrees latitude, then you need to apply the p-value of 0.5. So this gives you a guide on the p-value to use, which we are going to insert into the Blandly-Cradle formula. So Blandly-Cradle formula also always refers to mean monthly values, both for the temperature and the ETO. So the T mean, which is the mean temperature, is given by the T max plus the T minimum divided by 2, where T max is the summation of all maximum values of temperature of the month, then divide by the number of days of the month. Then T min is the summation of all the T minimum values in the month, then divided again by the number of days of the month. So that is how you determine the ETO. So I told you the crop water requirement is given by ETC, which is the crop water requirement. ETC is equals to ETO times KC. So ETO, we've seen you determine it based on two methods. One is evaporation pan, then 2 is the formula where we have used the Blandly-Cradle method. Now, the crop factor KC depends on the type of crop, the growth stage of the crop, and the climate. So if we look at KC and the type of crop, for example, a fully grown maize with its large leaf surface will be able to transpire and therefore use more water than the reference grass crop, because we said grass crop is the reference crop. So its Kc value will be higher than 1. Also, a cucumber that is fully developed will use less water than the reference grass crop, so its Kc value will be less than 1. Now Kc with the growth stage of the crop. A certain crop will use more water once it is fully developed compared to a crop that has just been transplanted, because when the crop is bigger, it has more leaf surface exposed. So more leaf surfaces definitely means more water is lost through transpiration. Again, if you look at Kc and the climate influences the duration of the total growth period and the various growth stages. So in cool climate, for example, certain crops will grow slower than in a warm climatic condition. Therefore, to determine the crop factor Kc, it is necessary for each crop to know the total length of the growing season and the length of the various growth stages. So those Kc values are always provided in the tables. I'll also attach the Kc values for purposes of ease in calculations. So Kc is dependent on the climate and in particular on the relative humidity and the wind speed. So the values indicated should be reduced by 0.05 if the relative humidity is more than 80%, that is high relative humidity, and the wind speed is low, that is less than 2 meters per second. The values should be increased by 0.05 if the relative humidity is low, that is less than 50%, and the wind speed is high, that is more than 5 meters per second. So if you look from the tables, you will do the necessary adjustments to get the most appropriate Kc values, which you can now plug into the formula of Kc. Of etc is given by Kc times ETO. So once you get the Kc, now you multiply by the ETO, then you determine your crop water requirement. But you need to factor in that the net irrigation requirement is given by the ETC minus PE, where now PE is basically the effective rain. So when it rains, rain is measured in millimeters. So if you determine that your crop water requirements, for example, is 6.5 millimeters per day, then now you will less the PE. If you get, for example, from the weather stations that the effective rain was 2 millimeters, then you take away 6.5 minus 2 millimeter, then you have your net irrigation requirement, which is 4.4, which is 4 millimeters of water, which you need now to apply to your crops. So again, you need to factor in that there's always, based on the irrigation system you are going to choose or you've selected to use, different irrigation systems have got different efficiencies. So you need also to adjust your irrigation amount of water you apply for irrigation based on the irrigation system efficiency. For example, if you're using drip, the efficiency is between 80 to 85%. If you're using sprinkler, it's between 70 to 85%. Then surface irrigation is between 50 to 70%. So for you to determine the actual or now the net irrigation system in overall irrigation, it should be the whatever you determined as the crop water requirement minus the effective rain, then you divide by the efficiency of the irrigation system that you've selected, so that at the end of it all you will be able to provide the amount of water that is able to meet your crop water needs. So then whatever the value you've determined, now you need to convert it into the practical field application. So to convert to volume for purposes of sizing the irrigation infrastructure, such as piping, pump, etc., normally we use a standard say the rule of thumb, where 1 millimeter is equals to 10 meter cube per hectare. So if you determine that your irrigation need is 5.5 millimeter, for example, per day, then you multiply by 10. So it will be 55 meter cube per hectare per day. So that is what you will use now to size your irrigation infrastructure in terms of piping, in terms of pump, and all that. So that now will come again as we go by. So that is it, guys. So next, we are going to discuss about the field capacity. So field capacity is basically the effect or the factor of soil into all this in determining the, in designing the most appropriate irrigation system. So stay tuned. Don't miss the next part of this video, because these videos, the way I said, they are building up, and it is important that you don't miss any section of these training videos. So for detailed design, installation and maintenance of your irrigation system, please contact us on the number on your screen. So thank you.